Alright, so today we're going to talk about Chapter 1.3. Chapter 1.3 is all about measurement. Now, to start with, we're going to talk about scientific notation. Scientific notation is a way of expressing a value as the product of a number between 1 and 10 and a power of 10. So if you remember from math class, product means multiplication. So we want to multiply two things. And a power of 10 is literally 10 raised to some number. So, scientific notation is a way of expressing a value as some number times 10 raised to some number. This is always what a number in scientific notation is going to look like. And the reason we use it is because it makes really large and really small numbers much easier to work with. Now, here's an example. Let's say we have the number 300 million, which just happens to be the speed of light in meters per second. What we want to do is really visualize how many spaces we have between each digit. And we want to put an imaginary decimal point right at the end of our number. We normally don't include that when we're writing numbers like this, but for scientific notation it's important to put it here so that we understand that's where our decimal point starts. Now, what I want to do is I want to imagine moving this decimal point over until I find a non-zero number that will be to the left of my decimal point. Now if you look over to the right, there's nothing over here. But if you look over to the left, we have a non-zero number way over here. So I'm going to move my decimal point over there. But I have to move it space by space. So I'm going to move it 1, 2, 3, 4, 5, 6, 7, 8 times until I get my non-zero number to the left of my decimal point. So I have now 3.000000 blah 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 blah. But that doesn't really help me. So what I'm going to do is I'm going to rewrite this in scientific notation as 3.0 times 10 to the 8th. And where did the 8th come from? That was how many spaces I moved my decimal point here. Let's do another one. Let's say we have 0.00086. Again, we want to visualize the space between the numbers, and we take our decimal point and we move it over until we have one non-zero number to the left. So I moved it over 1, 2, 3, 4 spaces. So now I have 8.6 times 10 to the negative 4. It's negative because this is a number less than 1. I had to move my decimal to the right. We'll get plenty of practice with this, so if you don't think you quite get it, don't worry about it just yet. Now, when we multiply and divide numbers in scientific notation, there's a really easy way to do it. To multiply the numbers in scientific notation, you multiply the numbers that appear before the power of 10 and then add the exponents. So, let's say that we have 3.0 times 10 to the 8th times 5.0 times 10 to the 2nd. We want to take 3.0 and 5.0 and multiply those to get 15. Then we would take the exponents 8 and 2 and add them together to get 10. So our final answer here is 15 times 10 to the 10th. Division is exactly the opposite. You want to divide the numbers that appear before the power of 10 and subtract the exponents. So in this case, we have 1.5 times 10 to the 11th divided by 3.0 times 10 to the 8th. This is going to end up being 1.5 divided by 3.0, just like we have simplified here. And when you do 1.5 divided by 3.0 in your calculator, you get 0.5. Now with the exponents, we want to subtract them. So I have 11 minus 8, which is 3. So our final answer here is 0.5 times 10 to the 3. This is much easier than trying to keep track of all of the digits and powers and putting it into your calculator. Now let's talk about measurement, because we've been dealing with some numbers, but none of these numbers actually tell us what they are. They're just numbers. And in science, your numbers always need to be labeled with what we call a unit. So scientists use a set of measuring units called SI, or the International System of Units. So in the United States, if I ask you, how long is that shoe? You would tell me in inches or feet. But in the metric system, or the SI system, length is measured in meters. Now you can see here we have a unit for mass, length, time, temperature, and a few others. We're going to add the most important ones to our concept chart in class. But these are the basic units that make up everything that scientists measure. Now there are also something called a derived unit, and a derived unit is one that's made up of a combination of other units. For example, area. Area can be calculated by a length times a length. Now we know that in the SI system, the length of something is measured in meters. So this is a meter times a meter, and anything times itself is that squared. So it turns out that the unit for area is a meter squared, and it's a derived unit because it has more than one base unit made into it. Now, sometimes the units we use aren't really that convenient. And to help us out, to help us express large or small quantities in a simplified way that's not scientific notation, we use prefixes. And a prefix indicates how many times a unit should be multiplied or divided by 10. You've probably heard of some of these: kilo, centi, milli, nano. You may have heard of a kilometer. A kilometer is literally a kilometer. It is 1,000 meters. Now, in order to use these properly, we need to use something called a conversion factor. And a conversion factor helps us change from one unit to another. So, if I want to convert 8,848 meters, which is the height of Mount Everest, to kilometers, I would need to use a conversion factor. So, when you use a conversion factor, you always start with what you know. In this case, that's 8,848 meters. And then you multiply by something that is equivalent. So if we look over at our chart over here, kilo means 1,000. So there are 1,000 meters in 1 kilometer. And the reason why we have meters on the bottom here is because we need the unit meters to cancel each other out so that we're left with kilometers. So 8,848 meters is 8.848 kilometers. We'll get more practice with these two. Now, precision and accuracy. Precision is a gauge of how exact a measurement is, whereas accuracy is the closeness of a measurement to the actual value being measured. So if we look at these two clocks, let's say it's 10:25. The digital clock reads 10:28 and the analog clock reads 10:09. So the more accurate clock in this case is the digital one because it is closer to the real time of 10:25. However, the analog clock is more precise because the analog clock has this little red bar that tells us how many seconds have gone by. The digital clock doesn't tell us anything about seconds, so it gives us less information. It is less exact. Now, when we talk about precision, we link it to what we call significant figures. And significant figures are all the digits that are known in a measurement plus the last digit that is estimated. So it's basically how good your measuring instrument is. The more significant figures you have, the better your measuring instrument is. So let's look at this analog clock here that tells us it's 12:45. We know for sure it reads 12:45. But we know that this little red handle is telling us something about the seconds we can't really see. So I'm going to go ahead and guess it's 12:45.30 hundredths of a second. Now if we look at this digital clock, it tells us it's 12:45 and 36 hundredths of a second. This number has one more significant figure than this number, and that's because this clock is more precise than this clock. It is a better measurement of time. We'll go over all of these again many times in class and get a lot of practice, but hopefully this is a good introduction to scientific measurement.